And good afternoon again. Welcome to what may be one of the last talks of the afternoon here. We are honored to have Zanie Blue with us to talk about the past, present, and future of virtual environments. Let's give Zanie a big hand.
All right, thank you, Ned. Ned was right to say present first because that's where I'm going to spend a bunch of my time. Hi, everyone. My name is Zanie. I work at Astral, where I build high-performance developer tools such as Rough, UV, and TY. Since I first started using Python, I've learned a lot about the power of tools to make getting things done easier. And part of the way that tools do this is by abstracting details from you, reducing the amount of complexity that you need to deal with to accomplish your goals. In the packaging space, virtual environments are a fundamental touch point for developers. And today I'll be talking about how virtual environments are increasingly abstracted and hidden from the user experience, as well as some of the motivations for that. So first, we need to understand what virtual environments are. Virtual environments are 20 years old, and I don't want to do an entire talk about their history, as I said. So I'll just kind of go over this quickly, but I do think it's important to contextualize like how we got to the point where we had virtual environments and all these tools that exist for using them. So what is a virtual environment? First of all, it's just a mechanism for isolating installed packages. So for example, you have foo v1 installed in this virtual environment and bar v2 installed in this other virtual environment. And there are various techniques to do this. I've listed some there. You can set the Python path. You can symlink the Python executable to change the sys prefix. I don't want to go into detail on the mechanics because it's actually not that complicated and it's kind of boring. We'll be focusing on the higher level user experience. So why do we need virtual environments? Well, first of all, most programming uses other packages. Code is hard to write, and there exists a lot of code that solves problems that you need, and these are usually distributed as packages. For example, Pydantic or FastAPI. So you need to install packages. I think we can all agree on that. And everyone's working on more than one thing at a time. Like either a bunch of projects or a project and a script or a bunch of scripts. And each of these things requires different packages, which brings us to our core problem, which is conflicting package versions. So if you're working on two projects, and we'll say one project requires foo, which requires Pydantic 1, and the other project requires bar, which requires Pydantic 2, you can't work on both of those projects in the same environment at the same time. Python does not let you install Pydantic 1 and Pydantic 2 into the same environment. If you've managed to do so, their modules would override each other and cause problems. Some languages do support this, like Rust, for example, can install multiple versions of packages within a single project, but Python cannot. This is kind of a fundamental constraint of Python's module system. So in order to work on these two projects, you need two environments and hence virtual environments. Another benefit of virtual environments is import boundaries. So on the right here, we have a script which declares a dependency on foo and it imports both foo and bar. Importing bar should be an error. However, if you're just using one big environment, this boundary will not be enforced, and bar could just get imported and the script would work fine. This is okay while working locally, but this is the kind of thing you don't want to have happen to you in production. So we have some motivations for virtual environments, and these problems have been around for basically as long as Python, so there are quite a few tools built around solving them. And here's my best effort at a timeline. I'm sure I'm missing a bunch of tools, so if you wrote a tool that's not on here, I'm so sorry. The slide's only so long. But I don't want to talk about all these tools, but I do want to talk about this timeline and how it gives us context for the way that the ecosystem has been evolving. So kind of at the beginning, these tools are working on the foundational mechanics of virtual environments. You've got virtual python.py, a blast for the past for some of you. Virtual env and working env, these are all around how do I create a virtual environment. And then you have things like setup tools and pip tools, all managing installing packages into environments. These are in contrast to some of the later tools, which are doing increasing abstraction of the environments. They're no longer concerned with how things are installed or the mechanics of creating the environments. They are building workflows on top of those foundations. And this is how tooling evolves over time. One thing I want to note, because I would feel bad leaving it out, is that Tox was introduced way back in 2010, and Tox is not concerned with the foundational mechanics. Tox is actually abstracting over environments, and Tox is really ahead of its time for that. However, Tox is really designed for library authors or package authors, and it's designed to help you run your test suite over multiple Python versions. The later tools that I want to focus on, that abstract virtual environments, are targeting more package consumers and end users, which I think is a much wider audience of the Python community. So now we know that what virtual environments are, let's talk about using them, and we'll use some of those tools from the previous slide as an example. This is kind of the standard workflow for using a virtual environment, and I think most of you will be familiar with it. First, you create the environment, then you activate it, and then you install a package. And that's great. We're using pip here just like as an example of like the most standard package installer I could think of. I call this an imperative interface because you install packages as you go rather than declaring them up front. I'll argue many times in this talk that declaring your dependencies up front is better, so let's get to it. There is support for a declarative interface in pip. You can have a requirements file with a list of packages. Here I'm adding rough to a requirements.in file and then installing that file with pip. You could add a bunch of requirements to that file for your project, but I'm just going to keep it simple here. The nice thing about declarative requirements is that you can share them with other people, and you don't need to figure out where you are each time you switch to a project. The project itself tells you what it needs. And there are other ways to declare requirements, such as a PyProject toml. We'll talk more about that later, but pip does have support for PyProject toml, of course. So why not use pip by itself for declarative environments? Because it's tricky. Like, for example, when you echo rough to your requirements in file, you can notice that we're not specifying a version of rough. And even if we specified a lower bound here, users can get an arbitrary version of rough. So you might have one developer on one version and another developer on another. Or you might be working with some version locally, but a different one in production. This is how we get incidents. You can lock the environment with pip. It has pip freeze to do this. We'll talk more about locking later, but basically locking is the basic premise that you can create a frozen set of requirements pinned to exact versions to help with reproducibility. The pip's mechanism for this is pretty simple in that it takes your current environment and dumps it into a requirements file. And this is helpful, but it relies on the state of the environment, which means that if you later pip install something that wasn't in your requirements in file, you now have to reason about whether or not it is safe to lock your environment. Additionally, returning to my point earlier about import boundaries, you can import FastAPI in your code even though it's not a part of your requirements file. Lots of people will point out this works just fine for them. And my qualm isn't that it doesn't work. It works fine. But you need to be constantly aware of the state of your environment, which adds cognitive overhead to development and prevents you from focusing on the things you really want to do. So I briefly want to talk about pip tools, which addresses a couple of the problems that I talked about in the previous slide. It adds a compile command, which is similar to pip freeze. It goes from requirements in to a requirements txt file, but it does so directly. It doesn't rely on the state of your environment. It also adds a sync command, which removes undeclared packages from the environment. So you can be sure that the environment matches the locked requirements. This means you can't import undeclared requirements. That's really nice. Additionally, sorry, this is a big improvement, but these steps are still manual. You need to know when to run them and be aware of the state of your environment. Additionally, pip tools only supports locking requirements for a single platform. So if you have developers on macOS and you're using Linux in production, you need to maintain 2 lock files for each of those platforms, and you can only generate them from that platform. This causes problems and isn't great for reproducibility. So I want to shift gears here to talk about the present of virtual environments. A lot of people are using pip tools in production still, so I don't want to like throw too much shade at that, but it was released in 2011. Like, what have we done in the last 10 years? And here I'm going to focus on UV, a Python package in Project Manager. I've been working on UV for the last 1.5 years, and therefore I'm very comfortable talking about it, so that's what I'm going to focus on. But it is worth noting that there are other tools that have introduced a lot of the workflows that UV builds on. For example, pipx, Poetry, Hatch, and PDM have all driven the Python ecosystem forward by improving packaging workflows. And most of the functionality that I'm going to talk about is available in one of these tools, or more. But as I mentioned, I really want to focus on UV because I don't want to have to explain the inners of Poetry to you. So first we'll start with one UV workflow, which is UV's project interface. So here is a basic workflow for getting started with a project in UV. Let's look at what happens here. First, we'll initialize a project. This creates a PyProject toml that we can use for declarative dependencies. This file will live in the project and be checked into source control and be the source of truth for what you require. Then we'll add a dependency. There's a lot that happens here. So under the hood, first UV will resolve the dependency that you've given. So you've asked for rough. So we will look at rough and all of its dependencies and compare those to the existing dependencies in your project to create a solution that is a comprehensive graph of all the versions that we need for your project. For rough, it's really simple. It's just a Rust binary and it doesn't have any dependencies. So the lock file will be really short here. But for other Python packages, it can end up being quite complicated. So after we do this resolution, for all possible platforms, we create a lock file that represents that resolution. Then we create a virtual environment, and then we install the subset of packages from the lock file that are relevant for the current platform. And all of this happens in a single command. After you do that, you can run the dependency. Notice that here we don't activate the virtual environment. We use UV run. UV run will activate the virtual environment for you, and you don't need to know which virtual environment is active at any given time. Another important point here is that we will repeat all of the steps that we did during UV add. If you were to delete the environment, we would just create it again and install the packages and then run rough. This means that getting started on new projects is really easy. If you clone a project off of GitHub that is using UV, you can just start UV running commands in it. You can UV run pytest and it will just work. In most operations, UV follows this pattern of locking and syncing. Before UV add, UV locks and syncs. Before UV run, UV locks and syncs. And this is the case for many commands. You can opt out of it, but the idea here is that you no longer need to think about whether your virtual environment is up to date to do your development. And part of the reason that UV can get away with this is because it's so fast. This happens on the order of milliseconds and is something that we've heavily optimized. I want to talk about one more project feature before moving on. because there are use cases where people will argue you need an imperative workflow to add a dependency. For example, this PDB++ debugger is kind of a personal choice. I don't want to declare this as a dependency of the project for all other developers. Typically, you would just pip install this into the environment, and it would just be around in the future. However, then you're back in this world where you need to worry about the state of your environment. Here, I'll advocate for using the with option to declare that you need an additional dependency for this invocation. And what UV will do is solve this dependency in isolation and then layer it in its own virtual environment on top of your project's virtual environment. And this is like a pretty complicated thing that you wouldn't want to do by hand, but UV can do this for an arbitrary number of dependencies. It can even let you do cool things like change the version of a single dependency for an invocation. Next, I'll talk about tool management. Tools are Python packages that provide a command line interface. A very popular tool in this space is pipx, and we've taken a lot of inspiration from them. You can kind of see this one-to-one. We support UVX rough. This will install and run rough. Rough is installed into an isolated and disposable virtual environment, and then invoked by UV. If you were to clean the cache, UV would delete that environment, but we do cache it to keep further invocations fast. If you get fancy, you can come up with an invocation that will show you the path to rough in our cache. UVX is just a shorthand for UV tool run, which is like one of many commands in our tool management interface. And so we support other things like installing tools, upgrading tools, listing tools, etc. I'll talk about tool installation next. So if you do UV tool install rough, we will also create this abstracted virtual environment, but this time it will not be disposable. And this is because we make rough available on the path. We create a symlink from your path to this virtual environment so that you can run rough without activating a virtual environment. If you do like which rough, you'll see it in the XDG bin path. And if you read the link, you can also, once again, like kind of recover where that environment is happening. But ideally, you would never have to think about this underlying environment. I don't really want you to look at it. I don't want you to mutate it. Just declare what dependencies you need and what you want to install, and UV will do it. Next, I'll talk about scripts. PEP 723 added support for inline script metadata, which is an awesome feature for the Python language. This is a great example about how you can change people's workflows by moving from an imperative to a declarative workflow. So here is a basic workflow for a script with UV. This is a lot like the project interface. Notice we are just using the script flag to denote a script that we are targeting. So if you initialize a script, what we'll do is we'll create a script with a main function. The contents of that don't really matter very much. The key is at the top where we are creating an inline dependency metadata section. And right now there are no dependencies, but in the next step we will add a dependency. The goal here is to have your script declare all of its dependencies up front. So when you add requests to your script, we will once again perform the resolution to make sure that the dependencies are compatible with each other. In this case, it's a little different than projects because we don't have a dedicated environment for each script yet. When you add that dependency, we will not create an environment and install it, but we will just make sure that it will work later. And then at runtime, first I modify the script to actually use requests so that my example is like reasonable. But then when you run the script, we will create the virtual environment, install the packages, and execute it. We were actually using disposable virtual environments for scripts at first, but we've changed that recently to make them cache to a consistent location so that editor support is a little better, but we'll talk more about editor support later. We look at scripts. If you do UV run like foo.py, we will inspect the script to see if it has inline metadata. If it does have inline metadata, we will create this dedicated virtual environment for it, but if it does not, we will just run in your current environment. So if you have a bunch of scripts that share the same dependencies as your project, that's totally fine. You don't need to use the inline metadata for those. As a little bit of a bonus, we support locking for script too. We added this pretty recently. Basically, this creates a lock file that's cross-platform in the same way as our project interface, and you can do all the same operations as you would then with all the benefits of reproducibility. So hopefully that was all familiar. You're just all using UV, and that was boring. But I hope that gives some context on how we're abstracting virtual environments today and how that can be useful. We've come a long way since my examples in the beginning using pip and pip tools, but UV hasn't solved all the problems of Python packaging. So let's talk about what else we should do. As we've discussed, I think declarative interfaces are really important for reducing cognitive load and improving developer experience. So if you're a critical audience, you might have noticed that UV tool install rough is imperative. Exactly something I'm arguing against elsewhere. I'll also argue this is entirely okay because you're not installing tools all day. It's usually kind of a one-off operation. There's not this cognitive overhead of state that you need to reason about. However, I do think that we could add a declarative interface for this, and that would be useful to a lot of people. We actually do generate this installation receipt when we install a script, install a tool. We put this in our tools directory and we use it to power features like uninstallation. We need to know where we put that rough sim link. And I think we could take this and we could just expand it a little into a file that's user-friendly, and this could just be your global manifest of tools you want. There's not a lot of work to do here. I think it would end up being very similar to a brew file conceptually. And then we just need to add commands to do these sync operations. So I just started with an easy one to soften you up. All I did was really kind of like wave my hands there and copy and paste our existing tool receipt. And I know you're all here to hear about the nightmare of Python packaging. So let's talk about a more complicated declarative workflow. PEP 517 allows packages to declare their build system. Installers can then install the build requirements in an isolated environment to build the source distribution into a wheel. So in this example, this is a build system for a package, and that package requires setup tools. This is not like the canonical example, I guess, because the big point of these build system declarations is that you can use things other than setup tools, which has been a big step forward for the ecosystem. These virtual environments are created behind the scenes by most package installers these days, and you don't know about it at all. So this is a great success story for hiding virtual environments for users, but there are some limitations. So, for example, some packages can't use build isolation. This is how you install flash attention today. This is a little complicated because the runtime torch version is used by flash attention. Flash attention links against that specific torch version, and so it can't declare it as a build dependency. So instead, you install torch first, as well as all of the other build dependencies of flash attention, because you can't mix build isolation and no build isolation, and then you install flash attention with build isolation. At this point in the talk, I'm sure you know that I don't like this imperative workflow, so let's make it declarative. And here's the declarative workflow, and it is still kind of ugly. It's nice that we moved all the dependency declarations into the Pi project toml, but if you don't run UV sync with just the build dependencies first before you do the second UV sync, it will fail. This also breaks things like UV run. Although we've made this declarative, we have not reduced enough of the complexity here for the user. You can't just run commands and have it work. So what I want to do is just have a way to declare an extra build dependency for a package. And here I'm arguing that you shouldn't ever disable build isolation. Instead, when UV goes to build flash attention at install time, it will look up the version of Torch in the lock file and install that into the isolated build environment for flash attention, and it will just work. So this isn't a tool-specific block here in this example. This isn't something we support yet, though we're working on it today. But long-term, I hope that we can show how this would work and then have the standards be updated to support things like this. I want to talk about external dependencies, but I don't have time to do so. I will wave my hands once again here and say that there are a lot of dependencies that your Python packages depend on, but they cannot be represented on PyPI. This is things like a C compiler or OpenSSL. These are terrifying things, but this is an open problem in the Python ecosystem, and I think that we should engage with PEP 725, which is a draft of how we can start making these things declarative. So another thing that I want to talk about for the future is improving reproducibility. We've made a lot of progress on reproducibility by encouraging the use of cross-platform lock files. And reproducibility has great properties. It reduces breakage, it improves auditing, and generally helps tools understand the state of your project. However, there are some places we can still improve reproducibility. And we're going back to build system declarations here. I put a slightly different example up this time. When Hatchling releases a new version, your build will use that version without any opt-in. This is because build dependencies are not included in the UV lock file. And build dependencies, as far as I know, aren't included in any lock file in the entire ecosystem. And this gets a little worse than just your project will have its build dependencies updated without your consent. If you have any dependency which requires a build and has build dependencies, they are unlocked and you will get new versions as they happen. What this means in practice is that when Setup Tools releases a breaking change that removes a feature that's been deprecated for 10 years, the entire ecosystem breaks. And this will happen to you even if you are not using Setup Tools yourself, and so the fix for it is to go bother maintainers of other packages. There's not much to say about the solution to this problem. It's a pretty simple concept. We should lock build dependencies. The implementation of this is going to be a little complicated because Python packages sometimes need to be built in order to determine their dependencies. This means at resolution time, before UV has generated a lock file, we need to be able to lock build dependencies. So the implementation of this will be a challenge, but it is something we're working on right now, and I hope that we can set the standard for other tools to support this as well. Last but not least, I want to talk about editors. So first for editors, they only the editors need to find a virtual environment in order to be useful. For example, the editor can't provide any language features until it knows what packages you have installed. There's not a standard location for virtual environments. Poetry puts them in some bespoke folder and has to write a VS Code plugin in order to help you find them. UV puts them in the project folder and hopes that's good enough for the editor to be able to find them. But one of the most popular issues on UV is complaining that VS Code can't find their dependencies. There's talk of a PEP to add a standard location, but I think users really shouldn't have to select their virtual environment when opening a project. This is the kind of thing that should just work. As environments are getting abstracted, it's less clear to users how they should be configuring their IDE. And if you're using declarative dependencies and have lock files for reproducibility, then it should be easy for the editors to just create environments for you on demand. Similar to this is, why don't my completions and type hints work in scripts? Well, editors don't support script metadata, and historically editors basically have an attitude that there is one virtual environment for the entire workspace. And I think that this really needs to shift to a model where the editor is choosing the best environment for each file in the workspace so that we can have things like support for script metadata. And when I say workspaces, I don't just mean scripts. UV is bringing multi-project workspaces to the Python ecosystem, and editor support for these also does not exist yet. Since they only support a single environment, import boundaries between projects in the workspace can't be enforced. I'd love to see innovation in this area. As a final question I want to pose, do editors need virtual environments at all? It's a little controversial, but I don't think the editors actually do need virtual environments. They need virtual environments today to analyze your dependencies for language server features and to allow you to execute your code. However, language servers don't need a virtual environment. They need type information. And installed Python packages can include a lot more than type information. For example, 99% of PyTorch is binary, not type information. Do we really need to make users download multiple gigabytes of data in order to start type checking their code? Yeah, you might need PyTorch downloaded eventually to execute your code, but we're in an increasingly distributed world. It's entirely plausible that you're going to edit your code locally, but always execute it remotely on some beefy server. As a closing note, if we want Python to continue to reach a greater audience in an age where programming is becoming increasingly accessible, we need to continue to invest in user experience. Best practices should be the default behavior. They should be automatic, intuitive, and easy. They shouldn't be more work. We've made great progress in the last 20 years, and I look forward to improvements on the horizon. Thanks.
Was an excellent talk there. I guess we really don't have time to take questions in here. Zanie's indicated that there might be time for some questions out in the hall. We thank you all for coming. The last block of plenary talks will be getting underway in about 14 minutes in Hall B. How about one more hand for Zanie's talk?